Good day, students. Welcome to math.serve.com. In this clip, we're going to be going over problems 28 to 31 of the Algebra 2 Trig Regents exam for January 2015. All right, let's take a look at number 28. It reads, solve algebraically for x, where 5 raised to the 4x is equal to 125 raised to the x minus 1. Now, one thing you want to note is that if you want to cancel out the base of an exponent using the inverse property of exponents, the log that is going to be used for the cancellation must have a base that matches the base of the exponent. Okay, so this is the property I'm talking about here. Let's say you have a to the x as your logarithmic expression. If I want to eliminate this base, I'm going to use log base what? I'm going to use log base a. So you notice that the base of this log matches the base of this exponent. These two functions cancel out and you're left with x. Okay, so that's how you do it. So the steps for this problem, number one, we'll eliminate the exponent, and then that will result in an algebraic equation, and then we'll solve it using the properties of algebra. Okay, all right, so let's go ahead and rewrite the problem. We have 5 raised to the 4x equals 125 raised to the x minus 1. Now I want to eliminate the 5, so I'm going to do the inverse, use the inverse. I'm going to take log base 5 of both sides of the equation. Okay, on the left side, I'll take log base 5 of 5 to the 4x. On the right side, log base 5 of 125 to the x minus 1. Now on the left side, you notice that this cancels out nicely. So you have 4x. Now on the right side, in order for cancellation to happen, the base of the logarithm must match the base of this exponent right here. Now this is 125. The question is, can you write 125 as a power of 5? The answer is yes. Recollect 5 times 5 is 25, times 5 is 125. So 125 is 5 to the third power. Okay, so we're going to express 125 as 5 to the third power, but freeze. We have an x minus 1 there before, so we have to use parentheses, put it back x minus 1. Okay, question again, why are we writing this 125? Why are we writing it as 5 to the third? The reason is because we want the base of the exponent to match the base of a logarithm so that we can now cancel out. Okay, so now we have 4x equals, now we want to distribute this 3 to the x minus 1. So we have 3x minus 3. To get x by itself, we subtract 3x from both sides of the equation. All right, and that yields x equals negative 3. And that is your answer for problem number 28. All right, let's take a look at number 29. It says in triangle ABC, determine the number of distinct triangles, sorry for the typo, number of distinct triangles that can be formed if measure of angle A is 85, side A is 8, and side C is 2. Justify your answer. Now, one thing you want to note is that in order for the dimensions of a given shape to be a triangle, the sum of the interior angles must be what? It must equal 180 degrees. Okay, and also the sine of any angle is never greater than 1 or less than negative 1. All right, if you remember your sine function, the sine function can either be 1, negative 1, or anything in between. That is the range of your sine function. Okay, so if you have a sine of an angle being equal to, let's say, 0.5, is this possible? The answer is yes, because it's between negative 1 and 1, right? What if you have sine that's equal to, let's say, 10? This is not possible because sine must be 1, negative 1, or anything in between 1 and negative 1. That is the range of the sine function, okay? So you want to keep that in mind. Now, in order to solve this problem, we're just going to go ahead and try and solve it. If we can solve it, then we'll count the number of solutions we have, okay? Um, and if we have any violations either of the range of sine, which is a number being greater than 1 or negative 1, that's a range violation, or the violation of the triangle angle sum theorem, which is that the sum of angles must be 180. If you have any of those violations, then that triangular solution is not valid. Okay, so eliminate it. That's basically what we're going to do. So we're not using any fancy formulas here. We're just acting as though we're trying to solve the problem. So now, whenever you're solving problems with triangles and you're given the measures in text form, what is the smart thing to do? What's the best way to ensure that you do not confuse your measurements and the labeling? You want to give yourself a visual, right? So you draw yourself a nice little triangle. I'm going to draw myself triangle ABC. Now, remember, uppercase letters are the angles and the lowercase letters are the sides. Okay, so little a must be opposite big A, little b opposite big B, and then little c opposite big C. So let's populate the measures. Little a is 8, little c is 2, measure of angle A is 85. Now, what law can we use to solve this triangle? Can we use the Pythagorean theorem, Sohcahtoa, law of sines, or law of cosines? In order to determine what to use, you look at the pairs that you have. If you have an SSS or SAS situation, you use law of cosines, okay? Now, if you have a right triangle, that's SS, okay? SS right triangle. What is this? You use Pythagorean theorem. Just two angles and you have to find the third side, okay? I'm sorry, so SSS. Okay, so SSS situation, use Pythagorean theorem. Now, if you're given a side and an angle, and it's right, then you're going to have to use Sohcahtoa. Okay, so if you're given a side and an angle of a right triangle, you use Sohcahtoa. All right. Notice I saved the one we're going to use here for last. If you have a situation like this, SSA, or if you have SAS, or AAS, guess what? For these ones, you use law of sines. Now, an easy way to know if to use law of sines or not is by looking at the pairs. If you have one complete pair of side and an angle opposite the side and an incomplete pair, that's automatically law of sines. Okay, so look here. Do we have a complete pair? Yeah, we have a complete pair, the A's, and an incomplete pair, the C's. So we're going to use law of sines here. Now, one thing you want to note is that whenever you're solving law of sines and you have SSA or ASS, this is known as the ambiguous case. What does that mean? It means that you do not have one solution. You can have either 0 solutions, one solution, or two triangular solutions. So that's what the problem is asking us for here. We have an SSA situation. How do we know? Well, check this out. This is side A, side, and angle. So when given side, side, and angle, SSA, you're going to use law of sines, and it's going to be an ambiguous case, okay? So let's just go ahead and try and solve this triangle. What are we going to solve first? So let me write down law of sines. What are we going to solve first? Well, let's write down our formula. It has two variations. Um, we want to find the incomplete pair, so we're going to find big C, okay? So how do we find big C? Let's write that down. Find big C. You want to start with what you're looking for. So uppercase, let me write down the variation we're going to be using here. Sine A over A equals sine B over B equals sine C over C. So we're going to use this first ratio, of course, because that involves what we're looking for. Sine big C over little c equals, now the next ratio we select must be a complete pair. The a's form a complete pair, so we're going to have sine A over little a. Okay? So you can have more than one unknown. If we apply this formula to this situation, we're going to have sine big C is equal to little c, which is 2, which is equal to sine big A, which is 85 over little a, which is 8. Let's go ahead and isolate sine C. To do that, we'll multiply both sides by 2. Please don't put the 2 after the um, argument of your trig function. Put it before so you don't have a grouping error in your calculator. So that cancels out. Then we have sine C is equal to this expression. We're going to put that in our calculator. All right, I'm going to be using a TI-83 plus here. Now, notice our angular measure is in degrees. So you want to make sure that you are in the right mode in your calculator. Radian degree, you want to make sure you're in degree. Degree has to be highlighted, okay? Now we're good to go. So we're going to compute parenthesis 2 sine 85. I put 58 there. 2 sine 85 divided by 8. And your answer is 0.66412. All right, so let's write that down. So sine C is approximately 0.66412. Now, how do we get C by itself? To isolate C, we're going to take the inverse sign, okay? We're not dividing, we're taking, not multiplying, we're taking, okay? So you take the inverse sign of both sides. So the inverse sign of sine C is approximately the inverse sign of 0.66412. Sine and inverse sign cancel out, so we have big C is approximately. Let's go ahead and plug that into our calculator. Now what I'm going to do is I'm going to pick up the answer I already stored before. Trying to find my calculator here. There you go. Okay, so second function, sine inverse sine of, so in order to preserve accuracy, I will call on my previous answer. So inverse sine of, second function negative gives us the cause of the previous answer, and we have 41.61. Okay, so angle C is 41.61. Okay, so before we proceed, one thing I would want you to note is that there was no range violations here. So why do we know that there were no range violations? Because the sign of the angle was between 1 and -1. So that's good. So no range violations here. Okay, so let's keep on going and see if we're going to run into perhaps a triangle angle sum violation where you cannot have, where you have a sum of angles that's more than 180. Okay, so now we're going to use the ambiguous situation. This is where the ambiguity comes in. When you take the inverse sine of a triangle in this situation, there are two candidates that can be used to construct a triangle. Why is that? Because sine is positive in quadrants 1 and 2 between 0 and 180, and we know that any angle in a triangle can be between 0 and 180. Okay, so let's go ahead and draw the two cases for you to see. So this angle technically is a reference angle, so I can call this theta reference, is a reference angle. All right, so we're going to take the two times where sine is positive, which is in quadrant 1. So there, let's call that the first measure. I'm going to call the first measure C1. Now that's 1. And then another case right here. Okay. Well, let me try and make it as perfect as possible. So there goes the first one. And then there goes the second one right there. All right, so in the first case, theta reference is equal to C1. We have two of them. So C1 is equal to theta reference, which is 41.61 degrees. All right, the answer we got, good. Now we can form a triangle there. This is the first possible triangular solution. We don't know yet. And then C2, another candidate, is where sine is positive and the angular measure is below 180. C2, I don't know why I wrote C1. C2 is 180 minus theta reference. How is that possible? Well, since theta is a reference angle, the reference angle is always measured from the x-axis, right? So this is another 41. But this is not the angle for my triangle. This is my triangle right here. Okay, so that's the second triangle. So to get C2, I just have to subtract 41 from 180. Okay, so this is the first triangle. And then the question is, what is the measure of this angle right here for my second triangle? That is C2. Okay, so to compute that, C2 is going to be, let's calculate that with a calculator. We have, clear that, 180 minus 41.61, and we get 138.39. Okay, so that's the second possible triangle, 138.39 degrees. Okay, so this one over here is 138.39. Now, what do you notice? It looks really messy, right? Everything is overlapping. This is my C1 and C1 and C2. C1, C2, and then it's hard for us to go ahead and solve this problem. So what is a smart strategy to help us avoid confusing ourselves with our own work? It's to separate the two overlapping figures. Okay, so I'm gonna draw the first case, C1, and draw the second case and see which of the, make sure that both of them are actually triangles that make sense. Okay, so this is C1 right here. It's not a perfect sketch. And then C2 is the other one, like that. Now the question is, do these two triangles make sense? Okay, so we're just acting as though we're just solving the problem blindly. So C1, this is 41.61. And then what was A? A is 85. So we can put, it doesn't really matter where we'll put it. We can put 85 right here. Let's call this 85 for A. Now for case 1, what is measure of angle B? Case 1. Remember, this is ambiguous. So for case 1, angle B is simply going to be 180 minus 85 plus 41.61. Is that a reasonable answer? Let's go ahead and compute it with a calculator. So we have, let's see, 180 minus parenthesis 85 for angle A plus angle C, which is already there. Let's call it back up. Enter, wait a minute, 180 minus 85 plus 41.61. I'm ending up with, oh, I'm sorry, I did it incorrectly. So we have 180 minus parentheses 85 plus, oh, there are two 41.61. Okay, I did case 2, we're doing case 1. Enter 53.39. So this angle is good, okay? B is 53.39. Do we have to keep on solving? No, we just want to check the number of solutions. Now let's jump to case 2. All right, case 2, is case 2 feasible? So let's go ahead and label it first. So we are using C2 here. What is C2? 138.39. Let's call this angle A, which is 85. And then we want to find B. Okay? So B, for case 2, where theta is in the second quadrant, is 180 minus 85 plus 138.39. Okay? All right, let's go ahead and do it. So 180 minus 85 plus 138.39. Enter. Uh-oh, we have a negative angular value. Does that make sense? It does not make sense. One thing you want to note is that what happens if I add 85 plus 138.39, I get 223. So what does this mean? I have already exceeded the limit just with only two angles. Remember, the sum of all three has to be 180. Only 2 is giving me more than 180, so that shows that this is not a triangular solution. Okay, that's why I'm having a negative angular value here. Remember, you cannot have a negative angular value. It makes no sense. So this is not a triangular solution. So not a triangular solution. Triangular solution, since B is negative. You cannot have a negative angular measure, okay? All right, so what does that mean in conclusion? There is only one solution. Only one solution, okay? And that's this one right here. They didn't ask us for it, so we don't have to solve it all the way. We just asked for the number of solutions. So there you have it. All right, let's take a look at problem number 30. It reads, the probability that Kay and Joseph Dowling will have a red-headed child is 1 out of 4, basically 25% odds of getting a red-headed child. If the Dowlings plan to have 3 children, what is the exact probability that only one child will have red hair? Now, one thing you want to note is that if two events are mutually exclusive, like your child is either a red-headed child or not, um, redhead means success, non-redhead means failure. The sum of those probabilities is always 1. Okay? So for example, in this problem, 1 out of 4 is success, right? The odds of having a redheaded child. And failure is going to be 1 minus 1 is going to be 3 over 4, basically, okay? So if you add these two together, these two probabilities, what do you get? You get 1, okay? So the closer a probability is to 1, the much more likely you are to be successful. And the further it is away from 1 towards 0, the much more likely for you to fail, okay? So 1 out of 4 is farther from 1, huh? So it's less likely that it's going to happen, okay? All right. Anyway, that's just by the way. Now, steps. What we're going to do here, first of all, we're going to write down the probability formula, the binomial probability formula, also known as the Bernoulli trial, which is provided right here. Okay? The probability of an event P occurring exactly R times. After writing down the formula, we're going to find the values of all the variables. It's very important you list these down and find out what they are before you substitute. It is very easy to confuse values here. So if you mix probabilities or number of trials or outcomes of specific events you desire, if you mix them up, you get the problem wrong. Okay? So let's go ahead and write down the formula first. Probability of R, that's the number of children that they want. R successes, so they want one child, is equal to, and let's write down the formula, how the total number of children that you're selecting from N, choose R. Well, let's just write it down, okay? NCR is equal to times probability of success raised to the R power times um, probability of failure raised to the N minus R power. All right. Okay, so let's figure out what our variables are. This is the tricky part. N, R, P, and Q. All right, so N, think about N as what you're choosing from. And R is what are you choosing, okay? So in this problem, they have three children and they want one to have red hair. So how many kids are in the pool of selection? You have three kids in all, right? So that's a total number. How many kids are they choosing to have one? I mean, how many kids are they choosing to have red hair? Just one, all right? So N is like the whole, okay? Number of trials, three tries. And how many do they want to have red hair? Just one. So out of three, they're choosing one, all right? Probability of success for having red hair is what? 1 out of 4. What does that mean? 1 divided by 4. Okay? Or you can write 0.25. It doesn't really make any difference here. You can use a calculator here. So probability of success is 1 out of 4 or 0.25. What's the probability of failure? Remember, if you add 1/4 to the probability of failure, you get 1. So to get the probability of failure, you simply subtract from 1, you subtract the probability of success, which is 1/4. 1 minus 1/4 is 3/4. Okay, or 0.75 or 75%. Okay, now when you do all this, you breathe a sigh of relief and you just plug this into your calculator and you will be good. Okay, so probability of 1 red hair, red red hair, a redhead. Make sure that's what it's called. Oh snap! What I call, yeah, you call it red hair, redhead, same thing. Okay, so is equal to out of three, you're choosing one. Probability of success is 1 out of 4 for one child. Probability of failure is 3 out of 4 for 3 minus 1, which is 2. Okay, so for success, 1 out of 4 for 1, 3 out of 4 for 2. And just plug this in your calculator and have your calculator do the work for you, okay? So let me show you how to do that with the TI-83 Plus. I assume you already know how to do this. So we have 3. I don't want to use that. Let me use my catalog here. Catalog and combination. There you go. N choose 3, choose 1 times 1 over 4. Now please put your parentheses in, your fraction in parentheses, please, or else you have grouping error. 1/4 raised to the first power or 0.25 raised to the first power, or just 0.25 or 1/4, times 3 divided by 4 raised to the second power. Enter, and your answer is 0.421875. Okay, let me see how many decimal places they are asking for in this problem. Okay, they didn't state any there, so I'll just put 4 decimal places. We have our answer as 0.42188. That's the probability of success. All right, let's take a look at number 31, which is very similar to problem 28. It reads, if log base x plus 1, if log base 64 of x plus 1, log base x plus 1 of 64 is equal to 3, find the value of x. Okay, just trying to make sure I say it correctly. So this is log base x plus 1 of 64, or you can say log 64 base x plus 1. Okay, so to solve an equation like this, one thing you want to note is that the inverse of a log function is what? Exponential. Okay, just as the inverse of exponential is log, the inverse of log is exponential. And their bases must be identical. All right, so let's say you have log base b of x. If I want to eliminate this log base b, I'm going to use exponent base b. So these two cancel out and I'm left with x. All right? Keep that in mind. Now, steps we're going to use for this problem solving process. First of all, we'll eliminate the log base x plus 1. That will result in an algebraic equation which will solve with the appropriate algebraic properties. Okay, so log base x plus 1 of 64 is equal to 3. That's our original problem. So first thing we're going to do is get rid of the x plus 1. So you're going to exponentiate both sides of the equation using x plus 1 as your basis of exponentiation. All right? So x plus 1 raised to the log x plus 1, a little log base x plus 1 of 64 equals x plus 1 raised to the third. Let's put our basis in parentheses since there are two terms being added there in that expression. Okay, take a look at the left side. It really looks messy. What on earth is this? Well, you have an exponent and a log base that exponent. So what happens? Cancellation happens since they are inverses. Okay, so we have 64 equals x plus 1 to the third. Now, there are two ways to solve this problem. One of them is extremely difficult and complicated, which involves expanding this and then setting it equal to 0 and using our calculators to find the roots where it intersects the x-axis. But the easiest or smartest way to do this would be to take advantage of the fact that 64 is a cube. Even if it weren't a cube, you don't want to expand this if you don't have to, okay? So what I'm going to do is I'm going to take the inverse of the third power. What is the inverse of the third power? It's the cube root, okay? So take the cube root of both sides and you see how powerful this approach is. So this cancels out with that. So we have x plus 1 equals the third root of 64, which is 4, because remember 4 to the third is 64. To finish this off, you simply subtract 1 from both sides. Subtract 1, subtract 1. Final answer is x equals 3. Okay? So that's that. Thanks so much for taking the time to watch this presentation. Really appreciate it. If you found this tutorial beneficial to you, please give us a thumbs up. We appreciate the positive feedback. Do not forget to subscribe to our channel for updates to the remainder of this review series. If you have any questions about this or the Algebra 2 Trig section of the Regents exam, just post a comment in the comment section below, and we'll be glad to address it as soon as possible. More clips can be found on math.serve.com. Thanks again for watching and have a wonderful day.